We'd like to move the D42 presentation. So please start.
Okay, thank you very much. Good morning, organizers, researchers, and participants. It is a privilege for me to present at this 2021 International Conference on Emerging Technologies for Communication. I am Chanan Atsawa Sirikunkit, the corresponding author of this research, a study of digital twin and its communication protocol in factories automation cell. First of all, I would like to give you an overview on what is digital twin. A digital twin is referred to as a virtual duplicate of a physical system with the use of smart sensors, the Internet of Things, or artificial intelligence to operate the model's properties and its behavior. Digital twin can be divided into four main layers: the physical, communication, virtual, and user layer. There are two keys to the success of digital twin implementation. First, the network aspect, making sure the message is delivered to the correct device. For example, between robots for physical communication, or between digital twin for virtual communication. Also between robot and digital twin for physical virtual communication. Second, the transport aspect, the way data were handled to ensure the reliability of the message between devices. Next is an overview on centralized vs decentralized network. For centralized network, digital twin would act as a centralized supervisors for all robots in the system, performing robot fleet management. Moreover, it provides high computing capability with edge computing. All robot would process simple tasks on board and send high data bandwidth to compute on the faster centralized edge computer. For decentralized network, machine-to-machine communication with no central controller would help robots to perform simple tasks better, unaffected by other device failure. Past literature has pointed out technologies that enables the development of digital twin in smart manufacturing cell. However, several literatures provide just a general framework, but do not really focus on the implementation of the technologies to real use case. Therefore, we would like to propose a real use case that significantly utilize digital twin. As an overview of our proposed system, the system consists of 5 subsystems: the mobile robot, the robot manipulator, the digital twin, the edge computing, and the communication router working in a warehouse. First, the mobile robot, which will be shown using iRobot Create. The mobile robot, equipped with LiDAR and cameras, are all connected to the Raspberry Pi. The Raspberry Pi would help iRobot communicate wirelessly through both MQTT and TCP/IP protocol. The onboard processors control the robot's trajectory using the position estimated by odometry. However, we relocate high computations tasks to external edge computing to increase the robot efficiencies. The LiDAR is used with the mobile robot to initialize its position by scanning and sending its absolute position to the edge computer for path generation. The raw data of the LiDAR scan is delivered to be processed at the edge computer. The camera is used to detect objects in workspace when mobile robot experience interruption. The edge computing will recalculate the optimized path, sending it back to the mobile robot to avoid obstacle. Second, the robot manipulator, which will be shown using Universal Robot 5. The robot manipulator is connected to the Raspberry Pi and the camera. The Raspberry Pi acts as an MQTT converter, since Universal Robot can communicate with the MQTT protocol. MQTT is required in order to publish all robots' IP address to the MQTT server for digital twin to subscribe. where it will be used for robot fleet management. After successfully connect to the digital twin, the robot joint angles are then able to transmit to the digital twin for real-time localization. The camera used to detect objects placed in the robot workspace. Next, the digital twin, where real-time data acquisition will be shown in virtual space. The digital twin. In digital twin, robots share the same map, and everything in the automation cell is up to date. We operate mainly with MATLAB Robotic System Toolbox. Next, the edge computing, which acts as an external computation for robot, assisting the digital twin. For example, in robot path planning, LiDAR scan analysis, or object avoidance tasks. Lastly, the automation cell, operating wirelessly with Wi-Fi 6 or FDMA 802.11ax router for scalable massive machine type communication, great network capability, high efficiency, and reduced latency. Aside from the benefit of Wi-Fi 6, to successfully implement digital twin, we propose a communication architecture. We use a combination of a centralized network and decentralized network, since each have their own benefits. We use MQTT and TCP/IP as our standard communication protocol for the automation cell. Each cell in the system publishes its dynamic IP address, distributed from the Wi-Fi 6 router to the MQTT server. The IP address of all robots was registered with MQTT, while the protocol used to send raw data was TCP/IP. Data were collected and transmitted to Python programming, and then sent to MATLAB for real-time simulation. When sending a package to the warehouse, the robot manipulator will request a mobile robot from the digital twin. Digital twin have a routing table which know the status of every robot and their IP address. The digital twin would be able to assign a vacant mobile robot to be connected to the robot manipulator. Then the manipulator will receive the assigned mobile robot IP address from the digital twin and made a TCP/IP connection with the mobile robot. They would decentralize themselves from the digital twin and communicate on their own, resulting in a lower latency between the robots. After successful connection between robots, the mobile robot would initialize itself using a LiDAR scan for its current position and orientation. Then the path was generated in the edge computing from the initialized position to the endpoint coordinate. This waypoint was sent to the mobile robot for execution in the physical space and sent to the digital twin for real-time simulation in the virtual space. Several experimental demonstrations has been done to validate the effectiveness of our proposed techniques. First, the demonstration shows the digital twin of the robot manipulator. With the help of MQTT converter, the manipulator and the digital twin could establish connection. After connection, digital twin would receive the joint angle from the universal robot. The localization and mapping of the robot manipulator can be seen in physical space and virtual space. The camera was used to create the workspace mapping. We identify each object using bounding box, finding the edge point of each object. Then we extract the center point, and when we extract the center point, the length, the width of the image in pixel to identify its size and location, which can be translated into our digital twin. Next, for this demonstration, the localization and mapping of mobile robot traveling in a fixed path, which can be seen in the physical space and the virtual space. Usually the movement of the mobile robot is a fixed path, which is an optimized route to deliver and receive cargo, except when there is an interruption. Next, the demonstration in the case of interruption, which requires edge computing to recalculate the new path. When the camera on the mobile robot detects an object, it will request the edge computing to generate a new path for the mobile robot to perform object avoidance as seen. This last demonstration shows an interaction between robots with machine-to-machine communication. When the mobile robot enters the manipulator workspace, the manipulator would directly be triggered by the mobile robot to prepare cargo for shipping. After the mobile robot receives the package, it will disconnect communication with the manipulator and head towards the station to deliver cargo. In conclusion, we successfully localized and mapped the robotic system integrating machine-to-machine communication in factories automation cell. Decentralized machine-to-machine communication and centralized digital twin offers many benefits as they support machines to work together, and system could be managed efficiently. Lastly, our proposed technique provides some prospect for the next generation technologies. Thank you very much for your attention.
Thank you for your presentation. Is there any question or comment?
So I have a question. Okay.
Yes.
Okay, please.
Okay, so thank you for the presentation. So maybe it's an excellent work because the implementation is the most important and difficult part of this kind of research, maybe. So so my question is about the bottleneck of the performance. So which part is the most dominant part to indicate the performance of the system? Which part is the bottleneck of the performance?
I think the things that affect the performance most is there are two things. First, the position and the timing. So for the position, since, for example, the mobile robot, it works with the encoder of the mobile robot. Therefore, as we continue our work for a period of time, the error of the position of the mobile robot start to increase significantly. And for the timing, since in communication there will always be a delay, therefore, if there is a delay between connection between the universal robot or the manipulator and the mobile robot, it will be difficult for them to deliver cargo, or it may be like the mobile robot will have to be there before, like be there before the cargo is ready. They have to wait for a long time, or maybe the mobile robot will not be there on time for the cargo delivery.
Okay, so but it seems it works well by seeing your demonstration. So yes. Oh, thank you very much, and I enjoyed your presentation. Thank you very much.
Thank you very much.
Is there any question or comment? Sorry, I have one question. Mobile robot's IP address is registered first. So IP address of mobile robot is not changed
Okay.
when moving.
Okay, so what we have done is that, so when each device in our system start to power on, the IP address will be a dynamic IP. Therefore, when like for example the mobile robot, that we have 5 mobile robot in our system. So one mobile robot is on, that IP address will never be the same for, like, for yesterday and today. the assigned IP address will never be the same. But when the robot starts to work, it will publish its IP address, the current IP address, to the MQTT servers for the digital twin to acknowledge what robot is in the workspace, and it can know the status of every robot and their IP. So it will be efficient for them to assign when the manipulator wanted to communicate with the vacant mobile robot.
Okay, I understand. Thank you very much.
There will be a routing
So
table.
I have another question. Okay, so short question. So,
Okay.
so why are you choosing the MQTT, not the co-op? So, do you want to use the sub architecture of the protocol?
Yes.
Yes.
We want to use MQTT since it will be like, we think it is more efficient for us to use MQTT because of the quality of service, the QoS. So we can ensure like that the message will be surely will be published on the MQTT server for digital twin to subscribe.
So in my understanding, MQTT is using the TCP as a fourth layer,
Yes.
maybe. Okay, thank you very much.
But MQTT, we don't require the IP address when we use MQTT. We just know the topic of where we want to publish. So since initially in our system no one know other IP address, but if the device which they want to know the IP address of others, they will subscribe to the server so they can know, like for example, the digital twin wants to know the IP address of the manipulator, they can subscribe to that topic.
Oh, interesting. Oh, that's the MQTT is the best choice for
Yes.
that purpose. Okay, thank you very much.
Thank you very much for the presentation. The time is over, so we'd like to move next presentation.
Thank you very much.